Okay, so in the previous video we talked about what limits are and how they're basically the value that the dependent variable of a function approaches when the independent variable approaches a particular number. And we looked at a couple examples. We looked at f of x equals x squared, and we looked at the limit as x tends to 2 of f of x. And we saw, I'm just going to briefly draw it. So we have a parabola kind of like that, and this is x equals 2, and we saw that as x got closer and closer to 2, both coming in from the left and the right, f of x got closer and closer to 4. We also looked at square root of x, and draw that here briefly. 5, 6, 7, 8, 9. And we here, so 1's on the graph. This is g of x equals square root of x. Then we looked at the limit as x tends to 9 of g of x. So 1's on the graph of g of x, so is 4, 2, and 9, 3. And there we go. Okay, so this is the point of interest here. 9, 3. We saw as we approached 9 coming in from the left, as we got closer and closer to 9, g of x got closer and closer to 3. The same deal from the right. So here we said the limit. So we can say here the limit as x tends to 9 of g of x is 3. And I forgot to write it here. For f of x, when it equals x squared, the limit as x tends to 2 of f of x. We saw that's 4. Okay, and we took a look at the greatest integer function as well. Quick recap. I'll just draw it here. You can assume that this is 1, 2, 3, 4, 1, 2, 3, 4. Well, it is 1. So this is x equals 1, x equals 2, x equals 3, x equals 4, y equals 1, y equals negative 1, x equals negative 1, and so forth. And you saw the greatest integer function basically looked like this. A bunch of stair steps with open and closed circles at the integers. And here we looked at x equals 0.9999. The biggest integer either equal to or smaller than that is 0. But when you get to x equals 1, the biggest integer smaller than or equal to that is 1. And that's why you have the open and closed circles. And because of that, the limits as you approach the integers from the left and the right are different. But for non-integer values, the left and right limits are the same. And we also mentioned that when the left and right limits are different, we say the limit does not exist. So the limit as x tends to 2 from the left is 1. So we approach x equals to 2 coming in from the left, limits 1. Oh, and this is of int of x, limits 1. And the limit as x tends to 2 from the right of int of x, we also mentioned that the minus here means you're approaching from the left. It doesn't have anything to do with negative values, and the plus here means you're approaching from the right. It doesn't have to do with positive values. So the limit as x tends to 2 from the right of int of x is 2. And because these two limits are equal, we can say that the limit as x tends to 2 of int of x does not exist, and you'll often see people abbreviate that as DNE, because mathematicians do love shorthand. Remember, I left off the last video saying that in this video we're going to look at functions where the limit exists but the function is not defined where that limit exists. So the first example we're going to look at is this function f of x equals x minus 3 squared. So first let's see how we graph that. Now to think about this, the way you'd go about thinking about how to graph it is like this. You want to see, so you know how f of x equals x squared looks, right? So this is the origin, and it looks something like this. This is x squared. So what happens when we want to graph x minus 3 squared? Well, in order for whatever we square to look like x, so we can see on the graph of x squared, just ignore what I was just saying earlier. We can see on the graph of x squared, the origin's on there, 1's on there, and 4 is on there. This is 4. Hopefully you can see that. But what you'll notice is if we want to, so 1 squared is 1, 2 squared is 4, 0 squared is 0. If we want 0 inside this, we're going to have to, for x minus 3, the quantity squared, we're going to have to input 3 for x. If we want 1 inside the parentheses, we're going to have to input 4 for x. If we want 2 inside the parentheses, we're going to have to input 5 for x. So, relative to whatever was happening in the x squared function, it looks like everything in the x minus 3, the quantity squared function, happens 3 units later, or 3 units to the right. So it should come as no surprise that the graph of f of x equals x minus 3, the quantity squared, looks like x squared only shifted 3 units to the right. So this is f of x equals x minus 3, the quantity squared. So instead of going through 0, 0, it goes through 3, 0. Instead of going through 1, 1, goes through 4, 1. Instead of going through 2, 4, it goes through 5, 4. So everything shifted 3 units to the right. Okay, but let's say we're not looking at this particular, exactly this function, but we're looking at something just like it. We're looking at g of x is equal to x minus 3 squared everywhere except or here for all x not equal to 3, and when x equals 3, g of x is undefined. So this graph here will look similar to the x minus 3 quantity squared, but will with one notable exception. At x equal to 3, it's undefined, so we have an open circle here. It's not defined here, so I just ignore that dot there. Okay, so it continues like so, but it's undefined at x equal to 3. But if you remember what we talked about in the previous video, a limit is defined as the value that the dependent variable gets really close to as the independent variable gets very close to a particular number. So here, and this is g of x. As x gets really close to 3 coming in from the left, g of x gets really close to 0. As x gets really close to 3 coming in from the right, g of x still gets really close to 0, even though g of x is undefined when x equals 3. But the limit, nevertheless, right, exists. Why? Because when you come in from the left, limit as x tends to 3 from the left of g of x equals 0, and limit as x tends to 3 from the right of g of x equals 0. Since these two limits are equal, we can say that the limit as x tends to 3 of g of x is 0. We can drop the left and right. And but remember, g of x is not defined where x equals 3. Now we're going to look at another type of function, and it'll be a variant of the inverse function. If you remember, the inverse function is basically f of x equals 1 over x. That's not what we're going to look at. We're going to look at g of x equals 1 over x minus 2. So if you remember, the inverse function, 1 over x, basically looks like this, and this is 1, 1 here. And this is negative 1 here. And so as x gets bigger and bigger, f of x gets closer and closer to 0. As x gets bigger and as x gets closer and closer to 0 coming from the right, f of x gets bigger and bigger. As x gets closer to 0 coming from the left, x gets more and more negative. And as x gets more and more negative, f of x gets closer and closer to 0. But that's 1 over x. So what do you think x minus 2, 1 over x minus 2 is? So what do you think g of x equals 1 over x minus 2 is going to look like? Well, remember here that whatever is happening to x is going to, whatever is happening to f of x equals 1 over x. Whatever is happening to 1 over x is going to happen to 1 over x minus 2 2 units later. So what I mean by that is when x equals 1, right, 1 over x equals 1. But to get this 1 in the denominator, when you're talking about 1 over x minus 2, g of x, you're going to have to input 3 for x. Okay. When x equals 2 in f of x, 1 over x equals 1/2. But to have that same effect when you're looking at 1 over x minus 2, you're going to have to input 4, or something that's 2 bigger than 2. So everything that's going to be happening to f of x will be happening to g of x, only 2 units to the right. So the graph of g of x is going to look like this, only shifted 2 units to the right. So basically this is 2, 0. And it'll look like this. Instead of 1, 1 being on the graph, you'll have 3, 1. Instead of negative 1, 1, you'll have 1, 1, because remember, or 1, negative 1, I should say, because 1 is 2 bigger than negative 1. But let's look at the let's look at the limit as x. This is x equals 2 here. Let's look at the limit as x tends to 2 from the right of g of x, and g of x is 1 over x minus 2. That's this graph. So this is x equals 2. As we get closer and closer and closer and closer to x equals 2, coming in from the right, g of x is going to get bigger and bigger and bigger and bigger and bigger, and we can say that's plus infinity. Coming in from the left, as we get closer and closer and closer and closer to x equals 2, g of x, 1 over x minus 2, is going to move toward larger and larger negative numbers. Okay, so it's going to become more and more negative. And so we're going to say the limit as x tends to 2 from the left of g of x is negative infinity. And some teachers may take issue with that because infinity is not really a number. And all this is saying is that as x gets closer and closer to 2 from the right, g of x is going to be bigger than any prescribed number. So even if you pick like 10 billion, you can find a value to the right of 2, but very close to it, that's bigger than 10 billion. And coming in from the left, if you pick a value, say negative 20 billion, alright, you can find a value really close to 2 but slightly less than it, or you can find a value of g of x when x is really close to 2 but slightly less than it, say 1.999999999, infinite number of 9s, that's more negative than negative 20 billion. So no matter what prescribed number you pick, you can always find an x value where g of x is more negative than it coming from the left and bigger than it coming in from the right. Now we'll look at another similar function, and that's going to be h of x equals 1 over x squared. So let's see what that looks like. Just go ahead and sketch it and then explain why it looks the way it does. So it kind of looks like that. It looks almost as if 1 over x, which is up here, it looks like this portion in the third quadrant has been flipped over the x-axis, but it's not quite right because the slopes are different here. Because here you're taking the reciprocal of the square, whereas here you're only taking the reciprocal of the number itself. This is the graph of f of x equals 1 over x. Okay, and this is h of x equals 1 over x squared. But the point is you plug in a negative value for x, you square it, you get a positive number, you take the reciprocal of it, you still get a positive number. And as you take, let's look at the positive side. As you take bigger and bigger positive numbers, you square them, you get an even bigger positive number, but you take the reciprocal of that, you get a number very, very close to 0. You take a very small positive number, you square it, you get a smaller positive number. You take the reciprocal of that, you get a massive number. Okay, you take a very small negative number, square it, you get a smaller negative number. You take you get a very small positive number. You take the reciprocal of that, you get a massive positive number. You take a huge negative number, you square it, you get a massive positive number. You take the reciprocal of that, you get a really tiny positive number. It's very close to 0. So this is how the graph of 1 over x squared looks roughly. Now let's look at the limit as x tends to 0 from the right of 1 over x squared. We're coming in towards 0 from the right, getting closer and closer to 0, and we can see that h of x, which is 1 over x squared, is going to get bigger and bigger and bigger as the closer we get to 0 coming in from the right. So we'll say that's positive infinity. Now let's see what happens. We come in from the left. All right. We'll see that, looking at it numerically again, take a really small negative fraction, square it, you get a smaller but positive fraction. Take the reciprocal of that, you get a massive number. And the closer and closer you get to 0 coming in from the negative side, the more massive a positive number you will get. So we say that the limit as x tends to 0, from the left of 1 over x squared. This is not negative 1 over x squared, so if that confuses you, maybe I'll put the left there, or I'll just rewrite the whole thing. Limit as x tends to 0 from the left of 1 over x squared is also positive infinity. And the issue here, infinity is not really a number, but because the left and right limits are both positive infinity, some people say here that the limit as x tends to 0, 1 over x squared is positive infinity, and others, depending on who you ask, may say the limit doesn't exist. But one thing's sure, that when we looked at the graph of 1 over x minus 2, as we got closer and closer to 2 from the right, we approached bigger and bigger numbers. But when we got closer and closer to 2 from the left, we got more and more negative numbers, and the left and right limits were not equal. Okay, so here, with no ambiguity, you can say the limit does not exist. In this case of 1 over x squared, depending on who you ask, some might say the limit does not exist. Some may say the limit is positive infinity. Because let's say we took, we wanted to find the value of h of x, 1 over x squared, when x equals 0.0001. Well, that's going to be the same as the value of h of x when x equals negative 0.001. And the closer you get to 0, the more zeros you add after the decimal point, whether they're positive or negative, h of x is going to be the same. So some people say this is positive infinity, some say it doesn't exist. We're going to take a look at one more limit here, and we're going to stick with the function h of x equals 1 over x squared. I'm just redrawing it here. Okay, and here we want to find the limit as x tends to infinity. So as x gets bigger and bigger and bigger and bigger, positive numbers, what happens to 1 over x squared? Well, from the graph, we can see that it looks like it's getting closer and closer and closer and closer to 0. So we say the limit as x tends to infinity of 1 over x squared is equal to 0. But then what happens when we want to see what happens to h of x, which equals 1 over x squared, as x gets toward bigger and more negative numbers, or bigger and bigger negative numbers, more negative, whatever you want to say. So that's the limit as x tends to negative infinity of 1 over x squared. And we can see that h of x equals 1 over x squared also approaches 0. So we say that limit is the limit as x tends to negative infinity of 1 over x squared equals 0. So hopefully that introduced you to a couple more types of limit problems, and we'll pick up in the next video where we left off here and go over some basic limit rules and properties of limits.